so it could maybe get to right here. So this thing, if it were in here, it would oscillate back and forth, coming up to here, and then coming back down to here. Actually, I don't know that it would oscillate because it would just get to here and stop. So it wouldn't oscillate, it would just get to there and stop. So that's at the total energy we're there. What if we lower the total energy down even one more time? If we lower the total energy down to 2 joules, now we have an interesting situation because our total amount of energy is 2, which means if our object was at x2 moving, it could move to the left or it could move to the right, but would oscillate between here and here, because it would come up here, stop but have a force to the left, go back, move to the left to here, have a force to the right, and go back. So this is a situation where it would oscillate, never reaching x1 or x3. That's a situation there. If the total amount of energy were just 1 joule, if the total amount of energy were just 1 joule, we could find our object at x4. But the thing about x4 is that, I'll write it up here. If I make our total energy 1 joule, at x4, this is 1 plus k. That means that the kinetic energy is equal to 0. This is an interesting situation because if you're at x4, you're not moving at all. If you got a nudge to the right, you would try to move to the right, but you see the way that this has a positive slope, so the force would be back. And if you move to the left, this has a negative slope, so the force would be to the right. So we call this stable equilibrium, where you couldn't go either way without being pushed back, as opposed to our previous one, which was unstable equilibrium, where if you went that way, you would go even further. So this is a stable equilibrium situation. The last thing I want to do with this drawing is I want to see if we can create a force position graph given this. So we have the same positions, and the force graph would be the same regardless of the total energy, because remember, the force is the negative slope of this. Okay? It's the negative slope. So let's put in where we see the forces that we know for sure. Here's 1, right? We know that between 0 and about halfway to x1, we know this is flat. So we know that if this is flat here, then the slope would be 0. Then at x2, we put a tangent line on here. We can see that the slope of the tangent line at the relative minimum is 0, so the force is 0 at x2. Same thing at x3. Same thing at x4. And here at x5, it goes to 0. So between 0 and on, or between 5 and on, it's 0. So what does that mean? Well, if the slope is if the force is the negative slope, let's look at this section right here. This section has a positive slope, which means the force must totally be negative. So it goes from 0, gets increasingly negative, and then goes back to 0. So what does that look like in that section there? And then this is 0 here, but the slope of this section is negative, which means the force must have been positive. And then same thing here. So this is positive slope, so the force must have been negative. And this is a large, this is large. So being able to interpret a force graph, or being able to interpret the potential energy graph to construct a force graph is very useful in understanding this relationship right here.